please come in. There are chairs here that people assume that we are full. I just wanted, before we start with the science, to introduce the new administrator for the Black-Hole Initiative. His name is Bill Nering, and he will show up in a minute. Here he is. Bill, before coming to the Black-Hole Initiative, was the coordinator of the US-Japan Relations program in the Weatherhead Center at Harvard. But since a very young age, he was very curious about the sky, and it feels good speaking to him that he's one of us. So we very much look forward to working with Bill in making the Black-Hole Initiative worldwide attraction. And one of the important goals that Bill will be working on, aside from managing the administration here, is construct a website which will include information about all the activities. For example, next week we pretty much use this space all week. Ramesh has a tika. I should also mention that Ramesh purchased a very capable computer system that has many units. So we already had a major investment, 250K or so, in a computer system that will presumably simulate better the environments of black holes. That's what we're hoping. So we'll learn more about it. Bill, did you want to say anything?
I just wanted to say it's good to be here, and I'm excited to work with all of you. My office is just around the corner here, so if I can help you in any way, please let me know. I'm just getting started, so be patient with me as I kind of get up to speed, but again, I look forward to working with you.
And Bill will get his computer this afternoon, so hopefully afterwards he can work with it. Okay, thank you, Bill. Thank you. And then the science.
Great. So we have a full schedule today. I'll keep intros brief, but this is Paul Chesler, who will give our first talk. He was a Pablo Fellow at MIT and the postdoc at Harvard, and now he's one of the inaugural EHI Fellows. And today he'll tell us about gravitational collapse and hydrodynamics in extreme conditions.
Good. So I'm going to tell you about two seemingly different phenomena today. One is hydrodynamics in hadronic collisions, for example, at RHIC. This is an event that happened at RHIC. And also gravitational collapse. Let me begin by reminding you about the basic rules of hydrodynamics, in particular relativistic neutral fluid hydrodynamics. Imagine you have some macroscopically large box of some relativistic fluid. It has some flow, some fluid velocity, and you can parse up that fluid into many, many smaller fluid elements that are each themselves macroscopically large compared to small length scales, and such that the fluid velocity in each cell is approximately constant. The sort of textbook assumption for deriving hydrodynamics, the textbook assumption that you find in Landau-Lifshitz, is that in this macroscopically large element, the fluid is in local thermal equilibrium, meaning that its bulk properties, its macroscopic properties, are described by a proper energy density and a fluid velocity. So it's bulk motion, if you will. And with that assumption of local thermal equilibrium, I'll get over here so I don't block you guys. You can write down an approximation to the stress tensor. This term right here is just the stress tensor of a local thermal ensemble right here. It's boosted, moving at some fluid velocity. It has a pressure given by an equilibrium equation of state in terms of the energy density. And of course, the system globally will not be in thermal equilibrium, so there will be some corrections to the stress tensor, which by assumption are going to be small. So the eigenvalues of this viscous part of the stress pi are much less than the pressure. So the equations of motion are just going to be the equations of energy and momentum conservation. And if you neglect this pi for the moment, you have 4 degrees of freedom. You have a fluid velocity, there's 3 there, it's normalized to 1 in magnitude. And you also have an energy density. So this system of equations closes. So these would be the equations of ideal relativistic hydrodynamics. And you can, of course, go beyond ideal hydrodynamics, and you can specify what this pi is. And the basic assumptions that you have to make are essentially that of Lorentz invariance, and that the only preferred directions are the fluid velocity and derivatives, gradients. And so if the system is slowly varying, smoothly varying, you can expand pi out in a gradient expansion in terms terms of derivatives of the fluid velocity.
One question. Usually there is also thermal conduction, and the temperature may not be in the direction of velocity, for example, the temperature gradient.
So this will be a relativistic system, though, so it'll take into account thermal effects in the stress tensor, right?
But you're making the assumption that all gradients are in the direction of velocity.
So yes, there will also be there'll be derivatives of the energy density in here.
Right.
Too. Right.
Exactly.
And they'll appear at higher order ingredients. Right. Good. Thank you. Right. So there can also be derivatives of the proper energy there. So in the local fluid rest frame, the expansion takes this form right here. At first order ingredients, there's only two structures that you can write down that are consistent with Lorentz invariance, just rotational invariance here. There's a traceless term, and then there's a trace term. And the coefficients are called the shear viscosity and the bulk viscosity. At second order ingredients, there's, I think, around 30 terms that you can write down that are consistent with Lorentz invariance, including terms that involve derivatives of the proper energy. And I won't write them down for you, obviously, although they have been computed in certain theories.
Those terms involving derivatives of the energy, you're assuming that the derivative of energy, is that what Avi just said? You're assuming that the derivative of the energy is small compared to what?
I'm assuming that
what's the dimensionless?
You're assuming that spatial gradients are arbitrarily small.
But it's relativistic, so it can't.
So they're arbitrarily small compared to microscopic length scales. So in particular, let me just continue on for a moment, and I think I'll answer your question. The transport coefficients at nth order generally scale like a microscopic scale raised to the nth power, like a mean free path. And so what this expansion is, this gradient expansion, it's essentially an expansion in powers of ratio of microscopic scales to macroscopic scales. So in the room, the microscopic scale is a mean free path, and the macroscopic scale is the size of the room. So in most ordinary circumstances, it's sufficient just to keep the first term.
There is another thing missing here, which is you need time derivatives as well to make it Lorentz invariant.
This right here is in the local fluid rest frame.
Okay.
Right.
But is it because it doesn't satisfy speed?
The causality?
Causality.
If you include second order corrections, it does.
Only time derivatives, right? Without time derivatives.
This was discovered in 2007 from the perspective of holography. If you include the second order derivatives, the theory is nice and causal.
Second order derivatives.
Well, it's a Lorentz invariant system, so once you write them down in one frame, they're going to be.
No, I don't mean that, but here you're only using spatial derivatives, and effectively what you do is you throw the characteristics.
There's no time derivative you can write down here in the local fluid
Correct.
rest
So
frame.
the reason that becomes a causal is by doing that expansion, you actually drop the way second order time derivative on the left hand side of your equations, and you cannot recover it by doing anything here.
You can actually. If you include second order derivatives here, okay, you make the theory Lorentz invariant and so on, it's causal. This is true. But you have to go beyond first order derivatives. All right, ultimately at the end of the day, this assumption of local thermal equilibrium is really equivalent to microscopic scales being much smaller than macroscopic scales. So a particularly striking example
But it didn't answer my question. Let's see. So uj dot is of order the gradient of P, right?
P?
The pressure.
Yes.
So you're not calling that small. The gradient of the pressure.
You're assuming that all gradients are asymptotically small compared to microscopic scales.
Yeah, but what is preventing me from adding a term here, the gradient of the pressure times ui? That would be consistent with the symmetry.
The gradient of the pressure times ui.
Which is related to gravity.
UI is
gradient of the energy.
No, but UI is 0 in the local fluid rest frame. So I can't do it.
No, ui isn't.
I'm in the local fluid rest frame. U is 0 in the local fluid rest frame. Its derivatives are not. Okay. But I got 15 other slides, so let me move on. So a striking application of hydrodynamics, relativistic hydrodynamics, comes from hadronic collisions at RHIC and the LHC. Now I'm going to go through this a little bit quick. At RHIC, what we discovered about 10 years ago is that when you collide two heavy nuclei, they're Lorentz contracted, they can produce a quark-gluon plasma, a deconfined state of matter that filled the early universe in the microseconds after the Big Bang. Remarkably, it behaves as a nearly perfect liquid and has the smallest viscosity of all fluids that have been studied in nature. The amount of time that it takes to go from this state, two bound states, to a liquid is less than or equal to 1 Fermi over c. That's the amount of time it takes for light to traverse the diameter of a proton. It's truly remarkable.
I think it takes less than that.
What's that?
You're saying it takes less than that.
The experiment puts a bound on how long it takes, and it's 1 Fermi over c or less. Okay. More recently, the LHC has done studies of smaller systems. They've collided, for example, a large nuclei with smaller nuclei like a helium. And they've even done this with protons, and they've seen evidence for quark-gluon plasma production there too. Okay, this situation is not settled, but the evidence is there. If you take it at face value, that means that you're producing droplets of quark-gluon plasma whose macroscopic scale is the size of a proton. That's remarkably small. Likewise, here the characteristic macroscopic scale is 1 Fermi over c. Okay? Now you should ask yourself, is this reasonable? If you look at what the characteristic microscopic scale is in QCE, you can estimate it from perturbative QCE. It's a mean free path. It scales like a strong coupling constant squared times the temperature, all raised to the -1 power. The temperature is about an inverse Fermi or so in one of these collisions, and if you extrapolate this result out to a strong coupling of order 1, the result that you get is that the microscopic scale is about the same size as the macroscopic scale, maybe even bigger. The fundamental question I want to address in this talk today is this crazy? Is it crazy to think about a system like this, whose size is basically the mean free path that's behaving hydrodynamically? Hydrodynamics has far fewer degrees of freedom than an underlying quantum theory does, than QCD does. So is it consistent to neglect microscopic excitations in a microscopically small system? Is the gradient expansion well behaved when the system is microscopically small? Now, I don't think there's any hope of recovering hydrodynamics for a system this small in the limit of weak coupling, because the microscopic scale is itself large. So the best hope that you have is to study the strong coupling limit because the microscopic scale becomes smaller. So sort of the pipe dream for us would be to compute the expectation value of the stress at strong coupling and compare its evolution to hydrodynamics. Of course, the challenge is that you can't do that. You don't know how to do it. We have limited theoretical tools. Things like lattice field theory, which is great for equilibrium thermodynamic quantities, but it's terrible for real-time physics. And perturbation theory, which is great for the limit where alpha is very small, but it fails miserably for alpha on the order of 1. So there's really only one thing you can do in this situation, and that is you idealize the problem to something that's simpler. You solve the spherical Colloquium approximation. So that takes me to black holes and holographic duality. So what is holographic duality? I'll give you several different answers to this today. So it's an equivalence between certain quantum field theories and theories of gravity in higher dimensions, namely string theories. It's a spherical Colloquium approximation in the sense that these quantum field theories all have extra symmetries that theories of nature don't have. Things like supersymmetry or conformal symmetry and so on. It's a weak-strong equivalence, meaning that in the limit where the quantum field theory is strongly coupled and impossibly difficult to study with traditional tools, the gravitational dynamics become classical. And so what this ultimately means is that we can study strongly coupled, very challenging quantum dynamics using the tools that were developed for numerical relativity within the context of astrophysics. And so my last answer to the question of what is holography, it's a unique and powerful tool that's capable of exploring an unexplored regime of quantum dynamics. Now I'm going to focus on one particular facet of holographic duality, and that is that of ADS-CFT duality, where you can take the dual quantum theory to be n=4 supersymmetric Yang-Mills theory. Essentially, it's a supersymmetric variation of the strong interactions. It's also conformal. I won't say much about it beyond that. You should regard it as a toy model of real quark-gluon plasma, the spherical column. The underlying dynamics that we have to study are simply Einstein's equations in 5 dimensions with a negative cosmological constant. And I'll take you through this one step at a time. The experts in the room will surely be depressed, and hopefully the lay people will be impressed. So, if there's any justice in the world, the ground state in the quantum theory should correspond to the maximally symmetric solution to Einstein's equations. And if there was no cosmological constant, that would just be 5-dimensional Minkowski space. The fact that there is a cosmological constant means that the maximally symmetric solution is anti-de Sitter space, 5-dimensional anti-de Sitter space. And so here's the metric in anti-de Sitter space. R here is the ADS radial coordinate. It's the extra dimension, if you will. Each slice of constant R is conformally equivalent to Minkowski space, a slice of Minkowski space. And as you go down to R equals 0, the geometry has this throat. And as you go all the way up to R equals infinity, there's a time-like boundary on the geometry. And in a very well-defined sense, that's where you should think of as the dual field theory. So how are our field theory observables then connected to the dynamics in this gravitational theory? I'm only going to describe that for the expectation value of the stress tensor. And you can think about that, well, an analogy is quite helpful here. So consider just electrodynamics. If I had a conducting plane in electrodynamics, and I put a charge beneath it, that charge will induce on the plane a charge density. If I now, for example, wiggle this charge around, it'll induce currents on the conductor. In gravity, if I put a gravitational charge into anti-de Sitter space, so a mass, it will induce, just via classical general relativity, a stress tensor on the boundary of the space-time. That's the stress tensor of Brown and York. And likewise, if I wiggle that mass around, it'll create gravitational radiation, and that will create currents on the boundary. This is all classical general relativity at this point in time. The holography enters into it in terms of the interpretation. It tells you to interpret this stress tensor on the boundary as the expectation value of the stress tensor in some quantum state. So for today, I want you to think about the problems I'm going to describe to you as, in essence, the gravitational analog of this problem right here. Okay? I'm going to be studying some gravitational dynamics in ADS and inferring interesting field theory dynamics from studying the near boundary asymptotics of the geometry. Okay?
And the math is proven. In other words, it's not just a conjecture. The relation between
everything I've said right here, with the exception of this,
no,
is, about this. Yeah, this is conjecture, but I think.
So how do you know it's right?
I believe it is, and everybody who's reasonable believes that it's
There's no proof that quantum field theory exists. So you could never have a mathematical proof.
But the entire program here is based or founded on this ability to move from one.
Nobel Prizes have been awarded for
45.
No, but why follow a program that is not proven? How do you know it's right? That's my question.
You could argue the same thing about QED, right? As Andy just said, QED doesn't exist as a formal field theory.
QED is known not to exist.
Right.
Well,
But proven not to exist.
Well, and yet Nobel Prizes have been awarded.
No, because there are experiments that agree with it.
Right.
But here, you're trying to make an analogy between two theories.
So I'm gonna do two things. First of all, I'm gonna end the question right here. But I will give you a little bit of an answer, and that is that there is a huge number of things that you can compute on both sides of the duality and compare, and you get the same answer. So no reasonable person in the field thinks it's wrong. So.
Preponderance of mathematical evidence.
I had another question. When maybe you saw it, when you show us the time evolution of things, are you going to assume that you have vacuum type?
Yeah.
So
it'll be ADS, the ADS value.
Correct. So this is not the real.
This is an excited state.
Correct. But you're going to solve only because of the time dependence of things that happen in the model. You're going to say how they project from the. on the 4D, right?
Ask me
Because
that
this
in
is not
10
supposed.
Ask me in 10 minutes. You'll see. All right. So I'm behind, so I'm going to go through this rather quickly here, and get to some of the punchlines. One of the more interesting things here is what do black holes in 5 dimensions correspond to? And the short and quick answer is that it has to correspond to a many-body state, because black holes have entropy and many-body states have entropy. So if I want to study a many-body state in the field theory, I'm stuck with studying black holes. The simplest black hole to study in ADS is a black brane. You can write down the solution on a postage stamp. It's the ADS Schwarzschild geometry. It's a uniform horizon, it's translationally invariant, and it has a boundary stress, which is just diagonal and satisfies the conformal equation of state epsilon equals 3p. If that is the geometry that corresponds to an infinitely static fluid, it's fairly simple to construct a geometry that corresponds to a fluid which is sloshing around. So to go back to slide number 2, take a box of fluid, parse it up into many small elements. This is a fluid on your boundary, where the fluid velocity is locally constant, and where the stress tensor is approximately just given by ideal hydrodynamics. It must be true that in the tube that extends into the 5th dimension, if you will, the geometry in this tube is given by just the locally boosted ADS Schwarzschild geometry that I wrote down on the previous slide. It's the geometry that corresponds to this stress, but now boosted with a velocity u, with some energy density epsilon. Okay. This was beautifully worked out in this paper right here. And you can compute the gradient corrections to Einstein's equations and find out that Einstein's equations are identically, in the long wavelength limit, they're equivalent to hydrodynamics. You can compute transport coefficients, and one of the most remarkable results that was obtained is that the shear viscosity to entropy density ratio is universal in all holographic quantum field theories. It takes the value of 1 over 4 pi as a dimensionless number. A remarkable result that actually matches up with the heavy ion data pretty good.
Isn't your first statement all?
What's that?
Isn't your first statement true?
Which one?
That if you write the equations in typing would look like pure hydrodynamics. Just by your definition of
one man's trivial is another man's.
No, but just by your definition of T right? This is the evolution defined like that.
It wasn't trivial to me. But, if it was, I would have wrote the paper. Sure. So I will say this: you can generalize this as Andy did to black holes, not necessarily in some holographic space-time, but just regular black holes, and study dynamics on stretched horizons and get the Navier-Stokes equation out. So I can't resist but show you a very cute example of fluid gravity in action. And that example I want to show you is of a turbulent black hole in ADS4, not ADS5, but ADS4. My recipe is I'm going to take a black brane, equilibrium black brane solution. I'm going to boost it in one direction. It's still an equilibrium black brane solution. I'll boost it now in another direction so that the boost is just modulated sinusoidally along the y direction there. And that will no longer be an equilibrium solution to Einstein's equations, but it'll be a good starting point, good initial condition. And so what you can do is evolve that system, and you can then extract the Brown-York stress from the geometry. The fluid velocity is the time-like eigenvector of the stress. And then you can construct a vorticity field from that and watch this evolution, and I'll show you a movie of what you get. So the vorticity at time 0 just varies sinusoidally in this direction, and here's what you get. You essentially get what you would expect from fluid mechanics. You get a nice turbulent flow that results from this. This instability that you get in the language of fluid mechanics is called a Kelvin-Helmholtz instability. If you stare at this long enough, you can convince yourself that, that the turbulent evolution is in fact an inverse energy cascade. That's what happens in 2 dimensions. And if you compute, for example, the power spectrum of the fluid velocity, you get Kolmogorov's k to the minus 5/3 scaling. These are all the usual things that you would expect from hydrodynamics attained from general relativity. Okay. So At the end of the day, I want you to think about the geometry dual to a fluid as an event horizon that's sloshing around, mimicking the dynamics of the fluid. Now, I will say this. I believe that there will also exist turbulent black holes in asymptotically flat space. It'll be interesting to search for them, and in particular, see if Kolmogorov K⁻⁵ scaling is in any way imprinted on the spectrum of emitted gravitational waves.
So this would be turbulence of space-time, basically.
Yeah, it's turbulence of space-time,
Which ends up being gravitational wave.
Yep. Right. Presumably. So back to the schedule at hand. Here's a holographic toy model of proton-proton collisions. Here's sort of an awkward-looking space-time diagram. Time runs this way. The spatial directions we live in are this way, and the radial coordinate is this way. The underlying dynamics are just Einstein's equations with the cosmological constant. So the simplest thing you can do is start an anti-de Sitter space and collide two gravitational wave packets. If those wave packets have enough energy, they can produce a black hole. Above each wave packet, there'll be some stress on the boundary. You'll see two packets of energy move together at the speed of light. They'll smash into each other. They'll produce some debris that fills the forward light cone, which will correspond to the black hole being created. The ring down of the black hole will then encode the relaxation of this matter right here to a hydrodynamic description. Okay? Again, think about this as the gravitational analog of this electrodynamics problem, where I'm colliding two-point particles beneath a conductor. I'll see two lumps of charge fly towards each other, they'll smash into each other, and then they'll fly apart. However, unlike the case of electrodynamics, in this case the system will eventually equilibrate because I have a black hole. It will eventually thermalize. So I'm going to skip over all the technical details about the numerics. It's a 5-dimensional numerical relativity problem. It's a shame I don't have the time, but this is the only 5D problem that's ever been solved that I'm aware of anyway, without any symmetry. And sort of remarkably, when you go through all the details, you can solve it on a laptop computer. You can solve it in about a month on a laptop computer. You have to clean out your fans, but you can do it. So here's a movie of the energy density on the boundary. There's an impact parameter along this direction here, and this is the collision axis here, the energy density. And so you let them smash into each other, they move at the speed of light, and they're dramatically altered after the collision event. The amplitude is severely attenuated, and there's energy deposited inside the light cone. You can look at the same picture now as a cartoon. Here's the energy density up here. This is the momentum density down here, T0I, and I'll put units on these plots here in just a couple of minutes. What I want to draw your attention to down here is that the magnitude of this plot shows the magnitude of the momentum flux, and the lines show you the direction that momentum is flowing. And so you see that after the collision, right here, momentum is flowing transverse to the collision axis. And that's exactly what you would expect if the system is evolving hydrodynamically. If there's going to be a pressure, there'll be a pressure gradient along this axis because over here it's vacuum. And so that will drive transverse flow. Now, I will convince you here that the system is evolving hydrodynamically. Hopefully I'll convince you. But before I do that, let me just show you the pressures. This is the pressure along the collision axis, and this is the pressure transverse to the collision axis at the origin. So initially, the pressures start out 0 because you're in vacuum. During the collision, the longitudinal pressure dramatically increases. And then the transverse pressure begins to increase as well. The longitudinal pressure even becomes negative for a brief period of time. The system is very far away from equilibrium. Nevertheless, at late times, both pressures become slowly varying and start to approach each other.
Is there something we're supposed to see in that little movie that shows us that somehow it becomes a hydrodynamic system?
No, not yet. You can't. It's not obvious from that little movie yet.
In hydro, you never have negative pressure.
It's not behaving hydrodynamically when there's negative pressure.
Right. So what is your equation of state?
So the equation of state is epsilon equals 3p. But it's not evolving hydrodynamically right here. So what I'm going to do, I'm not going to solve the hydrodynamic equations in motion because I don't have to. I'm lazy to. So I'm going to extract the fluid velocity from the exact stress, from the eigenvalue equation, I know all the transport coefficients because somebody else already computed them for me, so I can construct the hydrodynamic approximation to the stress to second order ingredients. And then just plot the hydrodynamic constitutive relations up here and just see when they start to agree. And that's when the system is evolving hydrodynamically. And so that's at about time 1¼ Okay, so shortly after the pressure is negative, not long after the pressure is negative. To elucidate the domain in space where the system is evolving hydrodynamically, I can define this residual function. It's the difference between the exact stress and the hydrodynamic stress, normalized by the pressure. It's dimensionless. So when this is much smaller than 1, the system is behaving like a fluid. And I can plot this. This is plotted at about time 1½ here in the xz plane. So this is the collision axis. This is the axis where there's an impact parameter. And this is the collision plane right here, the origin right there in the middle. And you can see that this residual function precipitously drops off to nearly 0 in this blue region right here. So you have a droplet of fluid that's formed. Okay. And the droplet size is, of course, just the same size as my proton, if you will. Now, is this a microscopically small droplet of liquid? Now here, I'm going to put units on things, and the natural unit to measure things in is the microscopic length scale. What is the microscopic length scale in strongly coupled plasma? It's in essence just a correlation length, okay? And without going into too many details, I'll tell you that the microscopic scale is some number times the proper energy raised to the -1/4 power. If the system was in thermal equilibrium, this microscopic scale would be 1/πT, where T is the temperature. Okay? So I plotted that microscopic scale here in the region where the system is behaving like a fluid at time 1, just a little bit after the hydrodynamics sets in. And you can see that the size of this droplet, the radius of it, it's about 2 to 3 times the microscopic scale. And the time in which the system starts to behave hydrodynamically is about equal to the microscopic scale divided by the speed of light. So we have a microscopically small droplet of liquid. So a few notable points here. While I am working in the spherical cow approximation, I deliberately focused on the low energy limit. And if you want to assign an energy here, you end up getting an energy that's on the order of about 20 GeV or so, which is far less than the collisions at RHIC and the LHC, where evidence of quark-gluon plasma formation is seen. Which means that this microscopic scale, if you take this at face value, is probably a few times smaller in the real-world collisions, which gives one some hope that, well, it's evidence that there's at least no theoretical inconsistency with applying hydrodynamics to these small systems.
That's like to say few, because it's a factor of 50.
Well, then you got to take the 1/4 power. Right. So there's no theoretical inconsistency with hydrodynamics seen at this level. This is a well-defined field theory, and arguably, this droplet of liquid is even smaller than that produced in real-world waters. Now, I want to conclude here. This is my final slide before I conclude by elaborating on the nature of the flow. This is not ordinary hydrodynamics. This is really hydrodynamics in extreme conditions. So I told you earlier that the viscous part of the stress tensor is a gradient expansion that you should regard as an expansion in terms of powers of a microscopic scale divided by a macroscopic scale. These two scales are basically the same. So how does this expansion actually terminate? What I plotted here is the magnitude of the first order correction, the viscous part of the stress, normalized by the pressure. It's a dimensionless number. And the second order correction, again normalized by the pressure, another dimensionless number, in the region where the system is actually evolving hydrodynamically. And so what you see here is that the viscous part of the stress, the first order gradient correction, is as large as the pressure. That means that your viscous contributions are as large as ideal hydrodynamics. And you can already see that in this plot here. In this plot here, by symmetry, the fluid velocity vanishes. which means that the anisotropy that you see here during hydrodynamic evolution is purely due to gradient corrections, is purely due to viscous corrections. And so the anisotropy here is about a factor of 5. The differences in the pressures are about a factor of 5. So that's remarkable. Nevertheless, the second order corrections in most of the region where the system is evolving hydrodynamically are about 10 times smaller than the first order corrections. So even though you have huge gradients, you have a system, you have hydrodynamics, the hydrodynamic gradient expansion being well behaved. The fact, however, that pi is on the order of the pressure tells you that there's no possible way this system can be in local thermal equilibrium. Okay? It's a system which is evolving hydrodynamically, evolving quite well hydrodynamically, but it is by no means close to thermal equilibrium. So with that said, let me give you some concluding thoughts here. Hydrodynamics is remarkably robust. There's apparently no need for local thermal equilibrium. If you go back to that, to my discussion in the beginning of the talk, where I discussed how to derive hydrodynamics or argue for hydrodynamics, if you go back and analyze that carefully, you will find that the need for thermal equilibrium was really more for pedagogical purposes than for necessity. All you really need are two things: a well-behaved gradient expansion and negligible non-hydrodynamic modes being excited. It's really all you need for hydrodynamics to work. And I think, one of the other take-home
messages... Is that the
messages...
same as you saying you don't need the thermal gradients to be a big force on the fluid? Is that
completely separate. The gradients of the energy density are allowed in here.
Temperature. Thermal equilibrium means the temperature is not constant. So
you can define something T equal to epsilon to the 1/4 and call it a temperature, but it's not actually really a temperature in this system. The system doesn't have a temperature.
Right. So are you saying that, so gradients of temperature give you forces, right? You're saying it's not, the temperature is not constant. So are you saying that those forces have to be, is that what you're saying? Those forces have to be small?
No, that's not what I'm saying at all. What I'm saying is that the gradients of all observable quantities, the proper energy density and the fluid velocity, have to be such that you have a well-behaved gradient expansion. It doesn't mean that the gradients of the proper energy have to be small per se compared to the fluid velocity. When I say the system is not thermal, I mean it doesn't have a temperature. For example, if I measured its temperature via photo emission and absorption, I would get a different answer for every frequency and wavelength that I looked at.
What about an equation of state? Do you need that?
You need an equation of state, but having an equation of state is not equivalent to being in thermal equilibrium. Okay? There's much more to being in thermal equilibrium than just having an equation of state. Now, in this example, it happens that the equation of state, the thermal equation of state, is satisfied even when you're not in thermal equilibrium. And in other holographic examples, that seems to be the case too. But that does not mean...
Normally when we do equation of state, for instance, we think of the pressure as an isotropic tensor. Right? But we're getting all sorts of anisotropic DIJs.
Right, but those are derivative corrections.
Those are the derivatives. So underlying there is an isotropic equation of state component, and then the derivatives are adding all these things.
It's all the derivatives that give you the anisotropy.
Right, and by the way, in fluid dynamics, the pressure, the equation of state is defined in terms of two thermodynamic quantities, not just one. The pressure is a function of energy density and temperature. I mean, only if the entropy is uniform, you can assume just one-on-one dependence.
Okay.
Which I guess applies to your case for some reason.
Well, I mean, if you're assuming that the gradients are asymptotically small, it is...
No, okay, so if you open a thermodynamics book, the pressure is a function of two thermodynamic quantities, or the energy density is a function of two thermodynamic. That's the equation of state, not of one.
All right. Okay. All right. So my last lesson that I want to leave you with is that Einstein's equations and numerical relativity are good for more than just gravity. We saw examples where you could study nuclear physics, turbulence. There are other examples, including examples from condensed matter physics, like superconductivity, superfluidity, and so on. Of course, you can also turn this the other way around and say that things like fluid mechanics are good for more than just fluid mechanics. You can learn something about black holes too. And I think that's interesting. So, thanks, guys.
in what we call classical hydrodynamics, there are many situations where we have breakdown of exactly that ratio expansion. We have macroscopic and microscopic scalings to be comparable. And yet the system evolves hydrodynamically, like shocks or function waves, quantum discontinuities. The reason being that there are conservation laws that determine what happens to the left and to the right, where your particular approximation breaks down. And when you care about how to connect the initial and the final result, it's real conservation laws that tell you what happens, but you can never predict them in between. What you showed here seemed to me to indicate something similar. You're not saying that you can predict hydrodynamically, just solving hydrodynamics, the detailed time evolution of the dynamics, but what you're saying is that you can tell me what the final, if you do the pure hydrodynamic calculation and the full calculation, then you're going to get from the same initial conditions, the same final conditions, but even though you might mess up the in between. Did I get that right?
No, what I'm telling you is that the bulk evolution of the system,
Can you define bulk evolution?
when you have a ball of fluid,
Yeah.
is governed by hydrodynamics. It's not just that you have some interface, some discontinuity.
No, not interface. I mean the beginning and the end. When you showed the time evolution of things, the hydrodynamics breaks down when the dynamics are really strong,
Right.
and then recovers afterwards.
Right.
This is exactly what happens if you take, a fluid element and you throw it through a shock. You're going to calculate correctly hydrodynamically from initial condition to final condition, but the minute it crosses the shock, you're going to get the wrong answer because that's not hydrodynamics there.
Sure.
It seems to me that this is the case here as well. What you're saying is that you can calculate correctly the transition through the situation where it's not hydrodynamic because it doesn't matter at the end of the day.
No, I mean, in essence, you're guaranteed at late enough times the system will evolve hydrodynamically. But what you're not guaranteed is that you're going to have a microscopically small droplet that evolves hydrodynamically. There's no guarantee at all that that's going to work. As a matter of fact, I think that before people did these experiments, everybody would have thought you were crazy. You would have said that a quark-gluon plasma would be performed in proton-proton collision.
What I'm saying is that if something happens, you consider fluid element crossing a shock or any the jump or any function wave, that you can guarantee that you can calculate the late time evolution hydrodynamically even though amplification of the shock.
You can guarantee you can calculate the late time.
Correct.
And late time behavior of hydrodynamics, but you can't guarantee that you can calculate it on microscopic scales after the event hydrodynamically.
In these very viscous systems of fluid plasma, is there something that corresponds to a Reynolds number?
Yes, and the Reynolds number, I mean, it's just the usual expression for the Reynolds number. In the relativistic system, it's the viscosity times the fluid velocity divided by the system size to some power here. And for a relativistic heavy ion collision, the Reynolds number is about 10. It's not particularly high, so you wouldn't expect turbulence.
And does it have an interpretation on the gravity side?
I think the interpretation is pretty much the exact same as it is on the fluid side. It's the Reynolds number. It governs whether or not you should have turbulent flow. So it's going to be the viscosity times the size of the system cubed times the fluid velocity in relativistic units. So that's about 10 for quark-gluon.
I got a naive question there. Do you basically say from the equations that a proton-proton collision for a fraction of the time behaves like a micro black hole?
Well,
because that's similar equation?
in the sense that it behaves like a fluid, you could say, well, it behaves like one of these black holes in the make-believe space-time in ADS5. You could make that argument, but it's certainly not a real-world black hole.
So you showed this beautiful movie of this Kelvin-Helmholtz instability, but I missed the point of that. Actually,
See it again?
yeah, the movie is great. Let's see it.
Let's make a poster and put it on,
Yeah.
on the
That
wall.
was lovely. We should have it on our screen.
Yeah.
So, but what exactly were you demonstrating with that?
I was getting you to ask a question.
Good. I've asked the question. Yeah.
Let me go back to that, wherever it's at. I was demonstrating to you, well, really what if you want to go deep into my mind, the psychology of it, what I really wanted to demonstrate to you is that this is more than just abstract stuff. You really can just solve Einstein's equations and get something that looks identical to fluid mechanics. So, and that's what you get in this movie right here. You get something that, if I would have solved the Navier-Stokes equation, you probably wouldn't be able to tell much of a difference here.
How do you generate this in Einstein's equations?
So what exactly did you do?
So I'll tell you again. I'll take an equilibrium black brane, boost it along one direction, but modulate that boost along the other direction. That's an initial condition, which is unstable. And it gives rise to, if I can stop the movement.
Then you evolve Einstein's equation.
Right, evolve Einstein's equations. And then near the boundary, there's a stress tensor induced on the boundary. I can extract that from the metric. You can also do this near the horizon too, as Andy showed. It doesn't matter where you really do it. You can extract the stress tensor from the metric. You can then get a fluid velocity from the stress, just a time-like eigenvector, and then construct the vorticity from that. Okay, and then let Einstein's equations do
If
it.
the amplitude is large enough, can't you make black holes there?
There's already a black hole right here.
Okay.
Right, so this vertical direction you should think of as in essence being a microscopic length scale. The amount of time it takes for an excitation to fall in here is a microscopic length scale. You should think about it as akin to a mean-free path in the underlying quantum theory. So the variations in the spatial directions here are very large. I'm sorry. Yes, very large compared to this length scale here. So locally, the geometry is just a boosted black hole. There's no time for any local structures to appear like that. Does that make sense? So,
Another question: when you run the movie, what do the colors mean?
blue means negative vorticity, and red means positive vorticity. So red is rotating clockwise, blue is rotating counterclockwise.
So this system was very high entropy.
Yes.
So you're saying that inside a black hole there's high entropy system. How do we know that?
I mean, the entropy is given by Hawking's formula.
So Bekenstein. You can think of that as the fluctuation in the angular velocity of the horizon.
Right. So what you could do, for example, take a black hole and now boost it along an angular direction in two different, and modulate the boost. So make it look like the cloud belts of Jupiter, okay? And then let it go. And I believe you're going to end up with a picture on the horizon that looks just like this. And as the black hole wiggles and oscillates and equilibrates, it's going to emit gravitational waves that it would be really neat to figure out if it has this scaling embedded in it.
This is an inverse cascade. So presumably, finally, all the power will go into the largest scales.
Right.
And if there is a net vorticity, you end up with a rotating black hole.
And if there's not a net vorticity, you'll still end up with a rotating black hole in the following sense. So if I have a two-dimensional fluid on a sphere, an inverse cascade is such that there's what happens is that in 2 dimensions there's an extra conserved quantity that is called the entropy. And what the entropy is, it's this integral of the square of the vorticity. So I'll be really quick with this. So the integral of omega squared is approximately constant. It's dissipated by viscous effects. So the fact that this is conserved means that if I have two vortices that are oppositely rotating, they can't come together and annihilate. Otherwise, you would violate entropy conservation. And so ultimately, if I have a black hole now, okay, that has some turbulent evolution, my belief is that the end state is going to be two vortices that are counter-rotating, if we can draw the picture correctly.
Don't you have
Not
ring down?
What's that?
A ring down of the fundamental modes.
There'll be a ring down, but the late time behavior will be hydrodynamic, and you should have.
That's not one of the steady state solutions.
It's not a steady state, but
so it will ultimately become a non-rotating black hole.
Right. And well, what's going to happen is that this is actually this is going to be
violated through viscosity.
So it's going to take a very, very long time to occur.
So would you expect the gravitational waves to be modulated by what's happening there?
I'm not going to answer that in any affirmative sense because I don't know the answer, but I suspect that they're going to mimic what's going on the horizon. I suspect that they're going to somehow encode this k to the minus 5/3 scale.
Okay, so
Thank you. We should put that on the screen.
Yes.
Okay, let's thank Paul again. So our next speaker today is Mark Reid. Mark is a senior radio astronomer here at the CFA, and he's an expert in all things VLBI, especially masers and galactic structure and supermassive black holes. So he's especially well known, for instance, for measuring the distance to our own supermassive black holes at JSTAR, the same one that the Event Horizon Telescope is working. So today Mark's going to tell us a little about the history, the observational evidence for supermassive black holes. Yeah, I think some more.
Is it actually
I avoided adding problems. We should try to yeah.
Okay, here we go. Well, this will be a lot simpler. Okay, and the basic question is, why do we believe that supermassive black holes exist from an observational standpoint? And I'm going to start, it's going to be largely a sort of a chronological talk of observational evidence for supermassive black holes. But I want to start with here's a picture of a globular cluster. This is a very dense collection of stars. There can be upwards of a million stars, and volumes that are as small as about 1 parsec, which is sort of the volume between us and the nearest star. And this we know is not a black hole. Okay, so that's our reference point for a system that exists that is very dense, but is certainly not a black hole. These things have been around since almost the beginning of the universe, so they are basically stable, although there's a lot of very interesting dynamics that goes on in these things. Okay, so I'm going to have a table here that I'm going to fill out during the talk. So we have an object, a globular cluster, its mass, say 10 to the 5th solar masses. Its radius, I'm doing it in astronomical units, distance from the Earth to the Sun, and so it's about 200,000 for a characteristic number. And I've got two densities here, sort of a Schwarzschild density of m over r, which would be c squared over 2g, and also a physical density in solar masses per cubic parsec. So, for example, the density of material near the Sun is about 1 in these units. And in the globular cluster, it's about 10,000. Okay, so let's fill in this. So let's go to very early radio observations. So in the 1950s, radio astronomy was really just getting going, and people were finding fairly strong radio sources. And this source, called Cygnus A, was the strongest radio source found in the constellation Cygnus, hence the A got attached to it. And when early interferometers were set up with higher angular resolution, it got a very surprising result. It's an interesting figure. And this is a model of Cygnus A. Okay, it's got a box here and a box here, saying there's emission in these boxes, separated by a little over an arc minute on the sky. And they found that the galaxy itself was centered between these two boxes. Okay, so now let me show you a more modern image of Cygnus A, done with a very large array in New Mexico. And you can see that basically that model was fairly good. And what is seen in this are two what are called giant radio lobes, one here and one here. They're centered on the galaxy, which is about at that bright spot there. That isn't that bright spot. And the galaxy itself is not much bigger than the bright spot here. So this is really kind of an astounding scale. The size of this system is roughly 100,000 parsecs. So these are some of the largest structures in the universe. And they actually get to be almost a million parsecs in size in some cases.
How big is the galaxy?
The galaxy, let's say it's, yeah, 10,000 parsecs of order. Kiloparsecs.
Right, those.
The galaxy, yeah, I'm trying to, you're
Those
right.
bulbs
That looks like a factor of 10, doesn't it?
No, it's a factor of 1.
That's 100 kiloparsecs. And the galaxy is 10 kiloparsecs. Anyway. I might have that wrong by 1 factor of 10. These things get up to be a megaparsec across. 100 times the size of the galaxy, let's say. Okay. It was understood very early on that this had to be synchrotron emission that we're viewing, so relativistic electrons spiraling around magnetic fields. And although we don't know the magnetic field strength, you can calculate what the minimum energy is in particles and fields for this whole system. And you get a rather astounding number. You get about 10 to the 7th solar masses times c squared. So that's a total conversion of 10 million stars like the sun into energy. That's the amount of energy that is in this system. Now, when this image was made, the most interesting part was this trail of emission. You can see here going to the center, and you might be able to see a similar trail on the other side. And basically, this is showing us that all of this energy was being produced in the very center, being transferred down these jets, lighting up these bright spots, and the energy sort of diffuses outward. When later on, observations were made with much longer baselines, with what's called very long baseline interferometry, where you get much higher angular resolution. One could see this jet going all the way down to the central parsec, 1 parsec of the galaxy, so distance from us to the nearest star. And this was the essential problem. How do you generate 10 to the 7th mc squared, m sun c squared, from a region that's about the size of, from us to the nearest star, knowing you can't do it 100% efficiently. So if you use nuclear processes, you can't even get 1% of the energy out. That would require channeling 1 billion stars like the sun through this very small volume in the center.
Wait, so how do you know? You're saying that all the energy is coming from the galaxy, going out like this little pencil?
Yep.
Now, how do we know that?
Well,
I don't know. It's not already out there.
Yeah. Why would? Yeah. What would have made this? It's very symmetric. They always have these nice little trails that end in these hot spots. It's not a mathematical proof. Extremely strong.
It looks fantastic from the
We also see superluminal motion. We actually see that it's
I can
moving
see that
stuff.
something is going on.
Yeah,
At
you see motion
at the speed of light.
Is that pencil very bright? So
No.
you know there's a lot of energy coming through the pencil?
No, it's fairly dim in this case. So it's not losing a lot of energy as it goes out here and deposits it here.
We measure its speed.
Yes, we measure, yeah, right. You can, with very long baseline interferometry, right at the center here, you can see blobs moving at nearly the speed of light. In fact, they appear to move faster than the speed of light, but they're not.
So we know that that pencil carries all the energy.
Yeah.
Why do they appear faster?
Oh, because geometry plus time dilation.
If you have a
So
blob,
they move towards-
if you have a flashlight moving at you, not quite at you, at the speed, near the speed of light, it appears faster. It's just like gravitational. It's very simple. Okay, so let's see, what else was I going to say? Yeah, the thin jets transport the energy, and nuclear processes would make it pretty difficult to do this. Okay, here's another galaxy. Shortly after, in the 1990s, after the Hubble Space Telescope was launched, they took this image of a galaxy called M87. It's a giant elliptical galaxy in the Virgo cluster of galaxies. You again see a jet. This one's quite dramatic, a lot stronger. You don't see much in the way of big lobes out there in the source. It's a slightly different type of object. And when the HST image, spectral imaging of the central region, right, the center there, was done, they could see what they'd like to interpret as an accretion disk, some disk-like thing that's orbiting, it's rotating. They saw, relative to the central position, they saw a redshift of 500 kilometers per second there, and a blue shift of 500 kilometers per second there. So it looks like it's possibly rotating. If you calculate what mass would be needed to make this rotate like that, you get over 2 billion solar masses, and the size scales we're talking about are about 18 parsecs. Yeah.
Do you only see one jet because it's coming in the picture?
Yeah, that's the feeling. Although it's a complicated one, yes. This should be Doppler boosted in our direction. That's the general reason, but the reason that we don't see a counter jet.
And do we know the angle that we're looking at?
No, we don't.
20 degrees is kind of a guess.
22 degrees is it?
Actually, in this source,
18 I've seen, but yeah.
in this
This
source,
is 27, right?
yeah, in this source which I worked on a long time ago, there's a lot of contradictory information about what that angle would be. But yeah, it has to be, you know, not too far off the line of sight and moving unit speed away. There's the Doppler boost this and Doppler dim in the backward.
And the width of the jet is like 60.
6 what?
How many degrees is the width?
The opening angle? I don't know. What do you?
It's not an opening, is it an opening angle? It doesn't seem to pick
Well,
up.
there appears to be like a shock in the jet here. It does grow right at the beginning. I don't have an image of that, where you can see it start narrow, sort of flare out, and then collimate. Okay, that's
And
getting.
there are, Mark, there are lobes on this one too, so on the other side, there are
Yeah, that's right.
relics all the way
There are
out.
some, but they're not as dramatic as Cygnus A's. Okay, so if this interpretation is right, the density in here is about 10 to the 5th solar masses per cubic parsec. We put that in our table, and you see we've made some improvement. It's a little more dense than a globular cluster, but of course that's nothing to write home about if you want to get to black hole densities, which would be these numbers here. So the bottom line here is what we think, I'll get to it later, what we think Sagittarius A star, the black hole at the center of the Milky Way, has about 4 million solar masses within about 3 Schwarzschild radii, quarter of an astronomical unit. Gives you these numbers. So we're a long way from those numbers. As you see, we'll get there though. Okay, the next sort of very interesting observation in the late 90s was the discovery of this galaxy, NGC 4258, which has what appears to be an accretion disk around it. It's very small, and it's illuminated, and the reason we can see it is that there are water masered in the accretion disk. So you have water molecules in this gas. It's a trace component in the gas in the accretion disk. But they're very bright. They're sort of a one-pass amplifier. Each sort of spot that we see on the sky is sort of a Jupiter mass of gas. That's amazing. And the amazing thing was, the image you got on the sky when you mapped it as a function of spectral channels was at one end you get spots here, and then there's other black diamonds, these here, and then these. That's exactly how it appeared on the sky. The scale is incredibly small. This is only about 1/10 of a parsec, so roughly the orbit of Mercury or less. Sorry, or more.
No, 0.1 is the edge of the sun.
Oh, sorry, parsec, not astronomical.
Parsec, yeah, right.
I'm off it. Still very small. 0.1 of the distance from the nearest star. It's about 3 milli-arc seconds, 3,000th of an arc second. And the amazing thing was these clouds of water maser gas are going away from us at about 1,000 kilometers per second. On this side, they're coming toward us at 1,000 kilometers per second. The stuff in the middle is actually moving sideways, so it has 0 Doppler shift. There's a spectrum down here, but that's all encoded in the information up here. The other thing that's important about these observations is that as you move away from the center here, the Doppler velocity drops, the rotational velocity drops, and it drops exactly as 1 over square root of distance. So it's perfectly Keplerian. The simplest interpretation is that we're seeing an accretion disk around some central object, and
these clumps could in principle be stars, right? Clouds of gas around stars. Because we get the water masers in our galaxy around stars.
yeah, my guess is it's not around stars,
You know,
but I can't prove that, yeah. The water masers in our galaxy are found near where massive stars form or where old stars sort of are dying, red giant stars. Yeah, good question. No one really knows that answer. Okay, so putting the numbers together of velocity and radius, you get 40 million solar masses in the center of this thing, and a radius of 0.13 parsecs. So the mass density you compute from that is 10 to the 10th solar masses per cubic parsec.
What's that? Sorry, in the solid line, there's a model of velocities.
Yes, I was going to.
What's
There
that?
You mean this line?
Yeah, what's that?
Oh, that's, can I explain to you later? It's going to take a minute. These are these features moving sideways. They actually do, you can actually see them starting to curve around. And this is what you would expect for, this is the Keplerian part here.
Right,
That's
part's
important.
okay.
That's the important one. The other one's a little complicated.
The other one,
It's nothing deep.
oh, all right. I can look
It's
at
exactly what you would expect from circular motion. So here's the new number. We got up to 10 to the 10th solar masses per cubic parsec, but we're still a long way away from a density limit close to a supermassive black hole. If you tried to put a star cluster, like that globular cluster, in the center of this, it'd be a big one with 40 million stars. You could put it in there, and it might last for maybe 1 billion years, but otherwise it would evaporate away. So this was pretty strong evidence at the time that this contained a supermassive black hole, but you couldn't really rule out an unusual, dense nuclear star cluster. Okay, so now to get much tighter limits, we go to our galactic center, the center of the Milky Way. And this is a radio image of the galactic center region. It was done in the early 1990s. And this whole region, before you had an interferometer that could resolve it, was called Sagittarius A, just like Cygnus was called Cygnus A, the radio source. In this case, it turns out to be a superposition of many objects. Okay. So the first thing you see in Sagittarius A is what's believed to be a supernova remnant. This sort of ring of emission around here. It's called Sagittarius A East, maybe multiple supernova remnants. The more interesting thing from this point of view is this dark region here, which I don't know if you can see it on this. Can you see that this is sort of spirally shaped thing? It's been called the mini spiral. And if you blow up the very central region of this, you get this image. And this is the first time we're seeing this radio source here. There's a compact radio source, which was unresolved when it was found in 1974 at about 1 arcsecond resolution. And it was called Sagittarius A, so for the strongest radio source in Sagittarius, and they put a star on it, an asterisk on it, indicating the compact source. This is the supermassive black hole at the center of our Milky Way.
What telescope made that picture?
That's the DLA. This is. Yeah, the Ballack and Brown paper does not have an image like that.
Oh,
They just found some very compact fringes.
because the BLA didn't exist.
That's right.
Yeah.
So this material here is kind of interesting. It's ionized gas. And in 1980, people spectrally mapped this region at 10 micron, actually about 12 micron wavelength, where there's a line of singly ionized neon. Measured the velocities, the Doppler shifts, and they found that across here, velocities went from plus to minus 260 kilometers per second. Pretty high velocity. And if you interpret that as gravitational in origin, you get about 1 million solar masses or a few million solar masses within about 1 parsec or so of the center of the Milky Way. Now, this didn't raise too many eyebrows because this is gas, and gas can be subject to non-gravitational forces. And so people didn't pay a lot of attention to it, but it was basically right. Later on, Genzel's group in Germany and Andrea Getz's group at UCLA measured motions of stars, and of course stars don't have any non-gravitational forces. They're not going to be pushed around by pressures. And these are the results they got for the velocity, actually the dispersion and velocity of stars as a function of distance from the center of the galaxy. Here we are at 1 parsec and 1/10 of a parsec. And they find this nice sort of Keplerian curve that you'd expect if there were a point mass at the center of this. And you can transform that to an enclosed mass versus radius, and you get a fairly flat curve out to about a few tenths of a parsec, beyond which it tails up because when you get that far from the center of the Milky Way, there's a sizable contribution to the mass from stars, like inside of a few tenths of a parsec, it looked like the enclosed mass was constant, again, consistent with a point mass in the center. Under the assumption that all of these stars were moving isotropically, they got a mass of about 2 times 10 to the 6th solar masses at the center, within a radius of a few hundredths of a parsec. That's an exceedingly high density now. You get a density now of 2 times 10 to the 12th solar masses per cubic parsec. And if you were to try to put a dark cluster of stars in the center to bind those motions, that cluster would probably only last about 1 million years now. And that would be pretty unusual. So this made a big splash, and rightly so. And it was touted as almost conclusive evidence that there must be a dark object in the center, and probably a black hole. Okay, but continued observations by Getz and Genzel were very interesting. Instead of just seeing the stars move across the sky, they could actually trace them. And one of these stars, called S2, this is an infrared image on the background. And if you blow up this very central region, this star was observed over about 16 years to have one complete orbit, a nice elliptical orbit. It started here, moved down like that. The techniques got better, the error bars got smaller, and it ended up there. And since this paper was published in 2002, the star has come all the way down here, and it's about to go past Pericenter again. The position of Sagittarius star, which I'll show you how we get, is right there. Okay, so this object indicates that there is about 4 million solar masses binding it in this orbit. And pericenter distance is about 0.0005 parsecs. I'll switch units to astronomical units now. So within 100 astronomical units, there's enclosed 4 million solar masses. So 100 astronomical units is sort of the extended size of our solar system. Imagine putting 4 million suns within that region. Okay. Continued observations. Other stars have been seen to move on elliptical paths now. And the most interesting thing is that all of the stars that are moving, here's that star we saw earlier, S2, they all have a common gravitational focus for the orbits. So they all indicate the same mass in the center, about 4 million solar masses, and a common focal point, which is right there. Okay, so putting the density limits on from these orbiting stars, because the radius is now very small, the pericenter distance is about 100 astronomical units, we get up to 8 times 10 to the 15th, almost 10 to the 16th solar masses per cubic parsec. Okay, so now you can ask yourself, the question, the infrared, I showed you an image, you actually don't see anything special, just a lot of stars. By the way, you can't see the galactic center optically because there's too much dust absorbing light from us to there. Okay, you saw nothing special on there, just a lot of stars. So where is the, what's going on at the focal position of all those orbits where presumably a black hole exists? So how do we find that? So I'm going to go back to that image I showed you a second ago. These are all stars around there. There's the focal position. And about 20 years ago, or 15 years ago, this was sort of the uncertainty you would get in the position for the radio source Sagittarius A star that we saw earlier. Where would it be on this image? And you couldn't tell to about this accuracy because it's hard to align the radio reference frame with the infrared reference frame. It's good to a few tenths of an arc second, at best, at these very subunit declinations. So what can you do to improve that? I mean, if you'll notice in here there are lots of objects, and maybe this one is the black hole, or this one. Hard to tell. Okay, so how to solve this problem? So actually, Carl Menton walked into my office about 15 years ago and said, here's a way to solve this. He said, here's an infrared image on the background in black and white. And all these stars that are circled here are red giant stars, so they're very bright in the infrared. They're big and they're red. Okay. And red giant stars tend to have radio emission from masers, from silicon monoxide, for example, or water, in their atmospheres. And so you can, with radio, with techniques with very long baseline interferometry, we can measure the position, say, of that star very accurately with respect to Sagittarius A star, because that's a steady point source at the center of our galaxy. So it shows up on the radio, just doesn't show up in the infrared. So what we do is we measure the positions of all these red giant stars in the radio relative to Sagittarius A star.
What is very accurate?
Very accurately, milli-ish arc seconds, milli-arc seconds. Okay? And so from this whole grid, and after doing this for about 15 years, we're able to locate the radio source Sag A on the infrared image to about 1,000th of an arc second, which is about 8 astronomical units. Pretty small. So it's in the center of that circle. As a reference point, the smallest dot you can see on this image is about 50.
It's smaller than Sagittarius A.
It's still bigger by 100.
Yeah, so the smallest...
Swatched radius is 0.1.
The smallest dots you can see on here are about 50 milliarc seconds. You can locate it to nearly a milliarc second. And it's way at the center of that, but you notice you don't see much there. Okay. But the main thing we found was that Sag A's position is coincident with the focal point of the gravitational orbits. That's the very interesting thing. So this point-like radio source is right at the center, gravitationally center of all the orbiting stars. So here it is on a blow-up from one of those previous images. These three things are stars, S1, S2, S3. That's the location of Sag A star at the dead center of that circle. And you can see if you subtracted out this diffraction limited image of this star, there wouldn't be much there. So kind of the amazing thing was that Sagittarius A star, this presumably 4 million solar mass black hole, is much dimmer than all these stars that are just floating around. It's really a very wimpy object. And I put on here, ask for mesh Y.
And you're getting the position there from what?
Okay, that's from this registration.
From the orbits?
No. Well, no. This is on here from the previous slide.
Oh.
So what we did is we give the infrared people the actual positions of all these stars to sort of milli-arc second accuracy. They have a grid of stars now where they know where they are, and they know that 0, 0 on that grid is the position of Sag A star, because that came from the radio. Okay, so they have now a grid. They can calculate the plate scale, the plate rotation, and distortion parameters, and figure out where any other infrared star is. To
So the other stars are both radio sources and infrared sources?
These guys are, yes.
Yeah. But, and then Sagittarius A star is just...
Yeah, more or less, yes. You can see it in the infrared occasionally, it flares up a little bit. Generally, you can't see it on the infrared images. But we can transfer the position. So that's why we know it's at the focal point of the orbits. Okay. So what else can we do? So in the last few minutes, I'll talk about radio observations of Sag A star. First one is in the title here that it's motionless at the center of the Milky Way. Now, how can we claim this? So what we've done is we've observed, here's a schematic of the Milky Way looking down on it with the galactic center here and the sun here. And the sun orbits the galactic center. It takes about 200 million years to go around. So if we exaggerate and we say we observe here and then maybe here and then maybe here, and we look at Sagittarius A star against some background quasars, very distant sources, we should be able to see the change in angle. It's a nearby object, in quotes. And so as you move around it, it'll appear to move against the background. You can do that with your finger if you want, right? Hold your finger up and move your head and you'll see it against the wall. It appears to move. The angles are small. They're milli-arc seconds. Okay. So here is sort of the observations that we have done over the last, since 1995. This is the plane of the sky. So north is upward and east is this way. The scale is in milli-arc seconds, and so it's 100 milliarc seconds from here to here. That's actually fairly big by our standards. In 1995, Sagittarius A star was here relative to some random background quasar. And we observed it about every year for a while, and then we spaced the observations out. You can see it just drifts down smoothly, very well fitted by a straight line, which is the red dashed line there. The interesting thing is the blue line is the orientation on the sky here of the galactic plane. So if the sun were moving exactly in the galactic plane around here, you'd expect to see this thing, an apparent shift in that position as we go around it. Okay? Now we see it's not quite the same. And that's because the sun is actually not quite moving exactly in the plane. It's also got a small velocity component out of the plane of about 8 kilometers per second. So it's going around at about 240 kilometers per second in the plane, and out of the plane, it's moving upward at about 8 kilometers per second. So its orbit is a little bit tilted, just slightly, with respect to the galactic plane. That explains this difference between the red and the blue lines.
Is that supposed to be most of the gravitational mass inside the sun's orbit?
No, not by a long shot, no. It's more like, I don't know, 10 to the 4 times it.
What? The galaxy is, yeah.
The mass is going to be 10 to the 11th solar masses or so. Counting the, well.
But that's the dark matter. But
Well,
just the
that gets us to 10 to the 12th if you go out to the very low range. Yeah, this is no, Sagittarius star's mass is insignificant compared to all the stars in the galaxy that we're orbiting with. So
no, inside our orbit.
Inside our orbit,
10 to the 4 or so.
Yeah.
So then why should it be so motionless?
Oh, no, the motion is around the galaxy.
So the sun is moving around the galaxy because there's a lot of mass in here. And now I'm going to tell you that Sagittarius star is not moving. Even though this is apparent.
So he wants to show that Sagittarius star sits in the center of the galaxy without motion, just sits there.
I know, but why should it just sit there? Why shouldn't it move in the
massive?
Yeah, it should move if it were not massive.
If you imagine Brownian motion and you have dust particles relative to air molecules, the dust particles move much less than the air molecules that bang on them, right? And then for the same reason, if you have a massive object like Sagittarius star compared to stars, it doesn't do much Brownian motion because it's massive.
Yeah, I mean, Avi's studied this. I've studied this. So. Think of the solar system. That's a simple case, except it's not Brownian motion.
Well, the solar system is different because there's not that much, because the sun is the main.
Right, but
it would be obvious if there was
you
nothing
put
else in
enough
there.
planets around the sun that constituted a solar mass in planets, so 1,000 Jupiters,
Yeah.
then the sun's motion would be Brownian at probably it would be given by essentially equipartition of energy. In this case, so for Sagittarius star, so we have, let's say, solar mass for the stars, and they're moving at 1,000 kilometers per second. And we, if you put in 1,000,000 solar masses here, it says the motion, the Brownian motion of the black hole should be about 1 kilometer per second. Those really crude numbers. I mean, actually, it should be about 0.3 of a kilometer per second. But what you can do is you can use this to estimate the mass. Put a limit on the motion of Sagittarius star after subtracting the effect of the sun's orbit. And that's getting near 1 kilometer per second. And you end up with a lower limit, an upper limit on the velocity, a lower limit on the, upper limit on the mass of about 4 times 10 to the 5th solar masses to be moving that slowly. If you put a star, any star that's observed at that position, it's moving at many thousands of kilometers per second. So this thing has to be massive not to be moving.
That's a lower.
A lower mass.
That's a lower limit, and that's about 10% of the mass sense gravitationally while the star is going around. So it's probably 10 times that. Okay. So, Shep's in the back with the Event Horizon Telescope, which you all know about. It's trying to measure the radiation coming out of the region around the event horizon of Sagittarius A star. Here's some early data that Shep's group has come up with. It's basically the strength of the signal you get on an interferometer versus its length or separation of the interferometer. And so basically this is going to smaller angles this way And when you start here and come down to about half the power, that says that the size of the source should be something like 1/2 giga wavelengths. So that's about 40 or so micro, not milli anymore, micro arc seconds. And of course, there are various models that would fit this. This is a Gaussian. Here's a ring coming through here, and it would fit the data too, sort of motivated by this calculation of what might be going on around the black hole's event horizon, as this stuff is Doppler boosted in front of you. So this gives you a size for this. If you now couple the lack of motion, the mass estimate for the radiative source, not the gravitational source, the radiative source has to be greater than about 4 × 10⁵ solar masses. Couple it with the size that they're seeing, which actually is a little bit smaller than you calculate for a non-spinning black hole ISCO. You get this number, greater than 10⁻23 solar masses per cubic parsec. And you can see now that's within about a factor of 6, less than an order of magnitude from sort of the theoretical limit you'd get for a black hole.
We actually bridged that as well. You're missing a line from LIGO. LIGO got to the scale of the horizon.
Okay. But not from Sagittarius star.
Not Sagittarius.
And not a supermassive one.
That's right.
So, I think, this history ends up with very compelling evidence that the galactic center harbors a supermassive black hole of about 4 million solar masses. And so the summary is basically this: that stars near Sagittarius star move on elliptical orbits with a common focus. The required central mass is 4 million solar masses within a radius of 100 AU. The position of the radio source, Sagittarius star, is exactly coincident with the common focus of the gravitational orbits to within about 8 astronomical units. The infrared emission from Sagittarius star is much less than a single star, probably indicating that it has an event horizon. Sagittarius star is motionless at the center of the Milky Way to something like 1 kilometer per second at the dynamical center of the galaxy. Its intrinsic size at 1 millimeter wavelength is about 4 Schwarzschild radii. That's sort of an observational number. And the required mass density is very close now to a theoretical supermassive black hole.
Is the 8 AU sort of error measurement, or
Yeah.
Or do you think it's actually bouncing around like that?
That's just measurements, right?
But do you think it's also bouncing around?
There's no indication of, for example, a binary supermassive black hole in the center of the Milky Way. Mostly from the fact how well this position of Sagittarius star fits that red line. That puts limits on what you could do for a binary component that would jiggle Sagittarius star around. And it's a complex little, it's a 2-dimensional calculation there. How massive is something and how far away is it? But it puts pretty stringent limits on anything.
Can you go to the next plot? Okay, is there something missing? Because, my simple thinking is that I have 2 points that draw a straight line, and I see here city is a curve. That means there's an equation somewhere.
Yeah, this is assuming the emission, which is calculated here, is a Gaussian brightness distribution, which this isn't. Except a Gaussian is a pretty good approximation to this.
Okay. Yeah, I wasn't looking at the scale. I mean the coordinates.
Coordinates. So these are in 10 to the 9th wavelengths. So it's resolved at 2 times 10 to the 9th wavelengths for the interferometer. Size is 1/2 to the 9th.
So generally for a telescope, the angular resolution is the wavelength over the size of the telescope. So it's basically the inverse of this number. So the lambda over giga lambda means 10 to the minus 9.
Yeah.
So 40 microarc seconds is roughly 10 to the minus 9. That's what it is.
That's amazing. To the resolution.
Yeah, oh yeah, yeah. To see, something at, a 1/10 of an AU scale at the center of the Milky Way is pretty amazing. See, that's fine in angular resolution. That's what happens when you can separate the telescopes all across the Earth and observe at a wavelength of 1 millimeter. So lambda is very small, wavelength is small, size of the telescope is very big.
So, Mark, you've seen these infrared maser stars, right? Do you actually also see them moving?
Oh yeah, yeah.
They do move, huh? Okay.
Oh yeah. They're just not quite as close. These arrows are their motions.
Oh, okay.
And so that's 200 kilometers per second. So, for example, this one is moving at a few hundred kilometers per second. And some of these are 150.
You also get the line of sight velocity?
Yeah, you get the
because of the maser.
Right. You get three-dimensional velocity. What you're missing is where in the central cluster they are.
One coordinate in the six-dimensional space, yeah.
And the orbits are like 10 years?
Well, no, these are going to be more like 1,000 years or something. The one that was right in the center of that earlier picture is such a tight orbit, it's 16 years.
How do you separate the motion of the lasers in the wind, the wind?
Yeah. So basically, yeah, what Eric is asking is these the masers form the circumstellar, so just outside the stellar photosphere, roughly 2 or 3 times the size of the star. There's a cloud of gas that's moving outward a little bit. It's actually pulsating, and so that. So the question was, if the masers say moving outward in that, would that affect this velocity? Yes, they tend to move outward and inward at sort of 5 kilometers per second. It's pretty small on that scale. The bigger effect is that you might have a spot, a bright amplification spot through one part of the atmosphere. One time you come back a year or 2 later, it might be from the other side. And that separation of the sides of the star is about 1 milliarc second. And so you sort of get an intrinsic half milliarc second uncertainty in every measurement. So that's why these measurements have actually been done now for about 15 years. So you have to keep doing these, it turns out.
Actually, you have the star pumps the maser, which is a cloud around. That's very interesting.
Yeah.
Mark, we do have a baseline of more than a century from the Harvard plates.
Yeah.
Have you checked?
Well, that's up. That's up.
Infrared.
Infrared, so they don't have.
Okay. You can't see this.
You can't see. That's the
This is what you'll see.
Over 1,000 years, we would see them moving around.
Yeah, that's too bad, but no. And they also didn't have 50 milliarc second
resolution.
Yeah.
Okay, I think in the interest of time, we need to stop, but let's thank both our speakers again.
Right.
Pretty impressive. They're on camera here.